In this tutorial we're going to take a look at total internal reflection. We're going to see what causes it. We're going to take a look at some of the applications of it, and we're going to be able to answer some questions on semicircular glass blocks and parallel-sided glass blocks. Okay, so let's get started. So we're going to start with a semicircular glass block like this one. The area around here is going to be air, and this is of course glass in here, which I'll just label out to the side. Glass. Shrink that down a bit. Okay, so glass, air. Now, we want to shine a ray of light into our semicircular glass block. Now the reason we're using a semicircular glass block is because if I shine light at the very center point here, pop an X on that. If I shine light right there, okay, that it doesn't matter where the light comes from, provided it keeps going to that X, shots on that, provided it keeps going to that X, it meets the glass block at 90 degrees on the outside. Okay, so this is 90 degrees here, this bit here is 90 degrees, and this bit here is 90 degrees, which means that there's no refraction on your way into the block. Okay, so all we have to do is consider the refraction that happens at point X. Okay, so let's do that. We'll start with a pretty shallow angle here. We've got a ray of light coming in. From our refraction, we should know that the first thing we do is draw normal. So let's get a normal drawn in there, like that. Okay, both sides, because the light will come from one side to the other side, so our normal runs right through. Now, we know from refraction that we're going to go from glass into air. As a result, we're going to speed up and we're going to bend away from the normal. So we wanted to go this way. And if there'd been no glass block, we're going that way, so we're going to bend away from normal. So we're going to go over here somewhere. At GCSE level, the exact angle we don't need to know. That's fun for next year at A level. Alright, so that's our incoming and outgoing. And again, this is no different to a normal refraction problem. The issue arises that if I make this angle a little bit bigger, then logically our refraction angle should come a little bit bigger. Now, let's get interesting. At some point around here, we're going to get an angle of refraction that runs like that. Okay, at some point we're going to create an angle of incidence in here, an incident ray that creates a refracted ray that runs right along the surface of the glass block. Okay, and this is critically interesting, and we call this the critical angle. The critical angle is the angle that creates an angle of refraction, of 90 degrees. Okay, so that's our critical angle. It's going to create an angle of refraction of 90 degrees. So what becomes super interesting is then, if I make this a little bit bigger, our angle of refraction has to be bigger than 90 degrees. But if our angle of refraction is bigger than 90 degrees, then the ray of light goes back into the glass block. More importantly, the ray of light never actually left the glass block in the first place, in which case it didn't refract. It didn't go from glass into air. So the refraction laws no longer apply. In fact, it simply bounced off one surface and came back. At this point, our reflection laws apply. It bounced off a surface, it didn't transfer from one place to the other, it simply all bounced off. In this case, we have reflection. We have no refraction occurring at all, and therefore we have total reflection. All of the reflection is inside, so this is total internal reflection. And total internal reflection occurs when the angle of incidence is greater than the critical angle. Okay, so total internal reflection conditions are that the angle of incidence is greater than the critical angle. Now this can only happen if you can make your angle of refraction bigger and bigger and bigger and bigger and bigger, which means that you need to be going from a more dense material into a less dense material. Because coming the other way, your angle of refraction gets smaller. It moves towards the normal. So we need to make it bigger than 90. So we need to have a situation where we're going from glass to air, or water to air, or something like that. So condition 2, in fact, really condition 1 is that you're moving from a more dense material to a less dense material. And if that's true, and the angle of incidence is greater than the critical angle, then total internal reflection will occur. Okay, so that's TIR basically. Let's take a look at what happens inside a regular glass block like this. Let's assume I've somehow managed to put some light in here. Okay, so under normal circumstances, that's going to hit up there. We're going to draw in our normal, something like this. We're going to refract out into the air like that, because we're speeding up, bending away from the normal. So this bit here, let's just be clear on what we're labeling. This bit here is glass. Okie doke. But if I make my angle sufficiently large, what I will find is that I will totally internally reflect along here. My angle of incidence should equal my angle of reflection. Now, because these sides are parallel, I can also say that this angle, down here, the angle of incidence in here, I might have to do a bit of freehand drawing, so this should be interesting. Okay, so this angle here is equal to this angle here. Those of you doing maths, this is a Z angle, isn't it? So if this angle was bigger than the critical angle, then this angle is also bigger than the critical angle. So I'm going to get total internal reflection happening here as well. So that's going to come off something like that. Now I'm on an anti-parallel side, or not anti-parallel, sorry, right-angled side to this. So this angle is probably not bigger than the critical angle. I'd have to go and do some trigonometry. I could work out what this angle is, then this angle. This is right-angled. I can work out all these angles and figure out whether it's bigger than the critical angle or not. And if it is, I get internally reflected this way again. And I can play the game all around. Or, alternatively, I will refract out into the air like this. That's the parallel block problem. Now, uses for total internal reflection are transmitting information over long distances. When you want to transmit information, binary code is kind of on, off, 1, 0. Normally what you do is you send electrical signals. But electrical signals can degrade over time. There's all sorts of problems with sending them long distances. If you have a really, really, really long piece of glass and you can make it super thin and flexible in a fiber optic cable, then what you can do is you can take light and you can bounce it with virtually no losses the whole way along until you get to the other end and the light comes out. So that's useful in things like fiber optic broadband. You want to take a bit of information from your computer, send it all the way across the world, super fast. That's how that works. It's also used in endoscopes. If I want to look inside somebody's body, and let's get ourselves a little person. So there's a head, there's a body, a couple of legs, why not? Okay, need a diet. Basic little person, super basic person. Okay, let's actually connect the arms to them. Okay, something's gone wrong with that arm, but oh well, good enough. Right, so we think this person has a little bit of a problem with them, so we want to take a look inside. Okay, we've got a problem with them somewhere around about here. Right, they're in pain. So option 1 is I take them to surgery, I cut them open, and their guts spill out on the table. Complications, lots of problems after that. Alternatively, what I can do is I can stick a glass pipe up their nose. So once again, we'll get the freehand drawing out here. Okay, I stick a glass pipe up their nose, down the back of their throat, all the way down and into their stomach. The light bounces all the way along and lights up their stomach. A second glass tube alongside it goes down as well. These are thin, by the way. Like, it's not ridiculous. And it's not glass that's rigid. This is bendy glass. Like, you know, the Christmas trees you get. Fiber optic Christmas trees. Second one goes along that, and first one lights up the stomach. Second one brings the reflection of that light back up. We stick a camera on the end of it, or a pair of binoculars, or ideally something that a surgeon can look through. Have a little look at that, and we can see inside their stomach. We can work out if there's something that we need to do something with in there. No need to cut them open. No need for general anesthetic. No need for any of the complications after that. Okay, so total internal reflection. Job done.